right. Hey, you guys. The last thing I have to do for this chapter is integration using tables, and this is section 7.8. It's pretty short. Integration using tables. Whoops, 7.8. There it is. There's another segment of this section that says and computer algebra systems. I'm not going to be covering that because we're not on campus and I can't force everybody to buy a computer algebra system. In other semesters, if you were on campus, you might use something like Maple or Mathematica. At ECC, we usually have Maple in the computer labs, and students learn to use a computer algebra system on Maple. You might have used that before for physics or maybe a different math class. It's possible that you have used some sort of computer algebra system before to integrate. But we will not be using it in this class, so you don't need to worry about that. We will be using tables, and unfortunately, this is not the most exciting thing. You will find it very useful when you're in Calc 3 because in most cases, your teacher is not going to force you to use a method of integration. As long as you can integrate, that's what matters. And in a lot of cases, if you can quickly just find an integral in the back of the book, in your table, then that's all that matters, is that you found it, you applied it, you're done with the problem. But in Calc 2, you need to learn all the techniques for integration. Okay, so I mentioned yesterday for me, I don't know when you're watching this, that I put these integration tables into your D2L page. So the ones that we're using, and these formulas are all going to be numbered, are in the back of your textbook. They're also in the appendices of your e-text. So your e-text will have appendices in it, and you can go into those, and there's something called integration tables. I showed that in class when we were discussing section 7.6 with approximating integrals. So you've seen it before. I'm going to be using the one straight out of my physical copy of the book, but I also put a PDF copy of the tables on D2L. So you have 3 different ways to access these, assuming you have a physical book. If you don't, you have an ebook. Otherwise, I put a copy of the integration tables on D2L. It's under content, handouts, and formula sheets, and then it's under table of derivatives and table of integrals. And that's what we will be using. So I have 4 examples prepared for you. I'm going to put up some homework. You can always let me know if you run into any issues on the homework. There are like 135 formulas back here. So obviously I can't give you an example for how to use each one, but I at least want you to understand how to adapt each formula to the examples that I'm giving you. Okay, so I'm going to say these are in your text appendix. Not test, text appendix. Way in the back or on D2L. Content, handouts, table of integrals. And you can download that if you'd like. You can download it and print it to use on your test. Otherwise, you can just access it however you need to online to use for your test. Example 1, this is the integral of dx divided by x times the square root of 2x minus 9. Now, in most cases, you're not going to find a formula that says dx over x times ax minus b. It's possible that in some books it's labeled that way. For us, we're going to have to actually look for a formula that sort of fits this form as closely as we can. What we're looking for basically is a constant in the numerator, or just 1 in the numerator for our formula, x to the first power in the denominator, and then a radical in the denominator with a linear term and a constant term. Now I'm going to share, actually, oh, you know what? I have it in here. I was going to say, it's probably going to be easiest if I sort of run through this table with you. So I will open this and then we can look at it together. I'm going to present that. There it is. So here's what it looks like, table of derivatives and table of integrals. And remember, you should have this written down now. I'm looking for in the denominator an x and then a square root of 2x minus 9. Oops, only works if I do that over here. Okay, so now if you're looking at the basic ones, these should all be on the basic sheet that you have already been given. So those are standard ones you use all the time. Okay, so now this involves a plus bx. Now you might be thinking like, yeah, we don't really have that. We have an a, but there's a minus sign, and then yeah, technically there's a bx. We're going to have to force it to fit a certain form. However, as you're looking at these, you don't see a radical in the denominator. So you're going to go down until you do see that. Now you don't have anything where you have x squared minus a squared. So you don't have a quadratic term. So you're going to keep going. This is the section that you want, starting with number 38. You're going to look through these and see what fits. Now, remember, I just want a dx in the numerator and an x in the denominator. I have that with number 43. So I'm going to write down number 43. Note that, oh, I'm not sharing that too. Hold on. Let's look at this and then we'll go back to my, my sheet here. Note that for number 43, there are two different instances. You have the case where a is positive and you have the case where a is negative. Well, we have 2x minus 9. That means b is going to be 2 and a is going to be negative 9. So we're going to have to think about this in reverse. So if we let b be 2 and a be negative 9, well, then a is going to be negative. And in that case, we're following the second definition for this rule. Now, if we had a being positive, obviously we use this one in the top line for number 43. But we're still using number 43. The difference is that a is negative. So I'm going to show you now how to fit this to the formula. Before I take this down, I'll just take it down now because I can still technically see it. And you should have it open also. See. Oh my gosh, I almost hit stop recording. All right, present. There we go. Okay. Wonderful. All right, so number 43 was the integral of dx divided by x times the square root of a plus bx. And this one is equal to 2 divided by the square root of negative a times the inverse tangent of the square root of a plus bx divided by negative a plus c. And this is in the case that a is less than 0. Okay, I'm going to ask you on your test. First of all, I'm going to specify that you're supposed to use a table of integrals to solve the problem. There are going to be maybe 2 of these on the test at the most. I just want you to show me you know how to use a table. Otherwise, you're not allowed to use tables of integrals on your exam. This is very hard to do. In person, I would have given you a separate page for your test, and I would have said, okay, this one's the one you can use your table on. This one's the one you can't. But it's hard for me to do that online. But I'm going to specify in the directions of your test. All right, for this one, use a table of integrals. Tell me which formula you used. That means tell me that which formula you chose. Give me the number. Make sure that you're using the integral sheet that I gave you so that you're not using some different number from a sheet that came from a different book, for instance. So you're going to tell me what the formula is. You don't actually have to write it out as long as you just give me the number for it, and then you're going to apply it. I would like for you to tell me at least what your variables are. So in this case, we're matching up the coefficient of x with b. So we're going to let b equal 2. And then a in our case is going to be negative 9. All right, so that's what this is going to look like. Let's go ahead and fill this in. Oh, by the way, notice that in your formula, you're seeing negative a. So that means that negative a is positive 9. I know a and 9 look kind of the same, so this already looks kind of confusing. But you know what it means. So let's go ahead and write our integral. So this is the integral of dx divided by x times the square root of 2x minus 9. So we're doing 2 divided by the square root of negative a. So 2 divided by the square root of 9. We'll simplify that in a minute. Times the inverse tangent of. Now we're using a plus bx. If you just want to use the 2x minus 9, you can. Don't feel like you need to go in order. I mean, just because I'm going to be applying this directly, I'll just use it in this order for now, and maybe in the next step, I'll switch it back. But as long as you keep the correct signs on there, it should not matter. So a is -9, and then plus 2x divided by, in the denominator, -a is +9 plus c. And then simplify this. So it's almost done. Just simplify it out a little bit. So this will be 2/3 times the inverse tangent of the square root of 2x minus 9 divided by 3 plus c. All right, first one's done. Now we will do another one. Example 2. This will be the integral of, in the numerator, we have the square root of 6 plus x squared. And in the denominator, we have x squared. And then we have dx. Whoops. Sorry. I accidentally clicked something. There we go. All right. So here's what we're looking at. I'm going to go back to my table of integrals. Let's go back and find it. Okay, now in this case, I have the square root of, now it doesn't specifically say ax squared. I'm sorry, it doesn't specifically say a squared plus x squared, but that's really what we're going for here. Oh, and by the way, keep in mind your book, your Sullivan text. I know I've complained about this before. They don't like to use u's. They do everything in terms of x, but you can always use a u substitution. Like for instance, if this was 2x squared, you could still use it with an x squared. You would just have to do a little u substitution to it. Not a huge deal, just something to keep in mind. Okay, so let's see. I'm going through my integrals. I have a radical with a squared plus x squared in the numerator. Well, there we go. And I have an x squared in the denominator. So those are the key things. And I am looking at number 52. By the way, every once in a while, I'll have an idea of a formula that I want to use, and I'll just use that one on the test key. And always some student will use a different formula that technically works. They just rewrite the function to make it match, and then they use that. So I don't want you to feel like there has to be only one way to do all of these, because depending on how you rewrite your integral, you can fit your function to use a different formula. That can happen. So I'm going to use number 52. So in my integral, I have a 6 plus x squared. So a is going to have to be the square root of 6, because if I want it to be a squared to be 6, it's just the way we're going to have to do it. So I'm going to use number 52. Notice that that is the, I mean, that's the only one I can see that would work in this case, where you have the radical in the numerator and x squared in the denominator. Go back here. So I'm going to write down number 52. So this is the integral of the square root of x squared plus or minus a squared. Sometimes you'll see that, and you'll just have to follow the signs in the formula so that they match the ones that you have. Equals negative square root x squared plus or minus a squared divided by x plus the natural log of the absolute value of x plus the square root of x squared plus or minus a squared plus c. Okay. In our case, we have a plus, so we're going to use that. Notice how these always say plus or minus, plus or minus, plus or minus. Every once in a while, you'll see a formula where they switch that. So like maybe the sign needs to change, and then it'll go minus plus. So make sure that whatever if your sign is on the top, keep whatever sign's on the top. If this is plus minus and that's minus plus, then you would use the minus for this term, because you'd be keeping whatever's on the top. That makes sense. I'm trying to look and see if there's one on your formula sheet that does that. I know it happens in some formulas. I don't see one right now, but you know, just follow the signs. Okay, so let's go ahead and match this up here. We're going to let a squared be equal to 6. So a is going to be the square root of 6. And then everything else is good to go in this case. So we're going to say that our integral, which is the square root of 6 plus x squared divided by x squared dx, is going to be equal to negative square root 6 plus x squared divided by x plus the natural log of the absolute value of x plus the square root of x squared plus 6 plus c. And again, the order of your addition, I mean, it makes no difference. Just, you know, as long as you're not changing anything, you should be good to go. Okay. Let's do a trig 1 or 2. So we've done 2 with radicals. 1 was linear, 1 was quadratic. Example 3. This is a good one to do just because sometimes you'll find that you actually have like a formula built into a formula. Number 3 is not exactly like that, but sometimes you'll have like another integral built into the formula, which you will see in example 3. So for example 3, we're going to look for the integral of e to the x cosine cubed e to the x dx. Now, this one's kind of tricky because you're not going to find a formula that exactly matches this. However, and if you want to get a good idea of what you need to rewrite this as, go back to your table and look at what's available. Sometimes we just have to see what there is, and then we sort of fit our problem to that integral, whatever it may be. All right, so I'm looking for something that has to do with a cosine cubed. Going through. All right, trig functions. Okay, so I don't have specifically a cosine cubed, but we do have a cosine to the nth of x dx. Okay, now we can actually fit ours to match. What you're going to note, though, is that this is not an x. So we're going to rewrite this by letting you... Oh, hold on, we're going to go back to number 89. I'm using number 89. I wish I could share 2 screens at once, but I cannot. All right, so I'm going to go back to number 89 and use it, but I'm going to show you how we're going to use it. I don't want to start writing a bunch of stuff and then you can't see what I'm doing. It'd be terrible. Okay. So we are going to let u be e to the x. Now remember then that du, the derivative of e to the x, is also e to the x. So du is going to be e to the x dx. Now, if you're wondering, like, how does that help us? Well, now we have e to the x dx as being du, and then we have cosine cubed u du. And now we can use number 89 with n equals 3. So I'm going to rewrite number 89 now that you've kind of seen what it looks like. I'm going to put it here. This is cosine to the n. I'm going to replace the x's with u's just because I feel like it's going to be really confusing if I don't. Maybe I'll write it with the x's first so that you get a good idea of exactly what it looked like, and then I'll switch them out just because it's going to look confusing for us. Okay, now here is what I was talking about. You've got a situation where you have an integral inside the formula for integration, which you'll find in this instance is not a big deal. It looks a lot worse than it is. Okay, so I'm going to rewrite this then as, and if we want, we can say that this is, we can go ahead and use n equals 3 and fill that in for right now, and then go back through and do the rest of it. So this will be cosine cubed of u du. Well, if we let n be 3 and we switch out x for u, so 3 minus 1 is 2. The x will be a u, and then we'll have sine u plus 2/3 times the integral of the cosine. 3 minus 2 gives us 1, so that's cosine u du. So rewriting it like that, this will allow us to kind of just fill in our u, and then we can integrate here, and then just back substitute. I'm going to back substitute all at once. I feel like the feedback I've gotten, at least from some of you, has indicated that that's best if we just stick with doing one thing at a time. Okay, so the first term's not changing in this instance. The second term, well, we know that the derivative of sine u is cosine u. Therefore, we can integrate this integral of cosine u as sine u plus c. And the really nice thing here is that we're almost done. We just have to back substitute. We got our integral in this form. We had cosine cubed u du, and as long as we have that, well, now we can just go through and substitute e to the x back in for u. I know, I feel like I just pulled a fast one on you because you're like, wait, did we miss something? What happened? We didn't. All we had to do was just guarantee that we had the form, which we did have the form. And then we used the formula to integrate. And once we integrated, we just back substituted out for u equals e to the x. So I'm going to give you another one where we have to use a u substitution, just because I feel like sometimes students forget to do that when they're using formulas. They think, oh, I should be using a formula. I shouldn't really have to do any work at all. But that's not true. Sometimes we do need to force our function to fit, either using a u substitution or maybe even using some other algebraic method. Okay, so the other one I was going to show you is example 4. This is the integral of the cosine of x times the square root of 100 minus sine squared x dx. Okay. So the goal here is to get this into a form that looks like something that would have been in your table of integrals. And I think even just having glanced at it for a few minutes, we should have a good sense of what's actually in there. We should be going for something like a squared minus u squared. In your table, that's going to look more like a squared minus x squared. But imagine if we let u be sine x and thought about this as being u squared. Then du is equal to cos x dx. Your cos x dx is du. So you can actually rewrite this as the square root of 100 minus u squared du. And then we just need to find an integral that matches that form, and that should be easy to find. So I think looking at this before the u substitution is kind of daunting, and you're kind of like, oh my gosh, a sine and a cosine, and there's just so much going on here. But just making this simple substitution really allows you to turn this into something where the form is so much simpler. Let's go back to our table of integrals. All right, so I'm actually not going to be looking at trig integrals in this case. You probably were thinking trig integrals to start with, and really you don't even see any trig integrals in here where you're looking at trig functions under radicals, so that wouldn't even apply. Oh, but we have exponential and logs down here. Hyperbolics you won't need to worry about. I'm not going to be assigning any of those. What I'm looking for is something that looks like the square root of a squared minus u squared, or in this case, the square root of a squared minus x squared. Oh, there we go. Look at that. Number 60. Number 60 is the square root of a squared minus x squared dx. So I'm going to use number 60. And then, of course, there are other variations on this. For instance, 61 has the x squared in front of the radical. 62 has an x in the denominator. 63 has an x squared in the denominator, so on and so forth. So you're seeing all these different variations. And I know you're thinking like, oh, these all look like trig substitution problems or even inverse sine problems. Yeah, of course they do. But that doesn't mean that you can use them throughout your test. You must show me your work. You must use methods from the chapter unless I have specifically stated to use the integration tables. So in most instances, when you see something like what we see in example 4, I would be expecting you to use some sort of inverse trig, inverse sine integral in order to actually finish that one out. But if I say use a table, use a table. Of course, I guess you can always check this using a table and see, make sure you got it correct, but make sure that you're showing me your actual technique that you're using from chapter 7 as you're working your way through, unless you have been instructed otherwise. I'll make sure that's really clear. Okay, back to our problem. Number 60 is the integral of a squared minus x squared dx. This is x over 2 times the square root of a squared minus x squared plus a squared over 2 inverse sine x over a plus c. Now, of course, we're going to let a be 10 because then we have a squared being 100. I'm going to write this one more time because I want to make sure this is written in terms of u's and not x's, because what we have right now is in the form square root a squared minus u squared du. Not a huge deal, but since our original contained x's, I just want to make sure that we understand that this is not just x. We're going to have to back substitute. Okay, so anywhere we see x, we're going to swap it out with u. So we'll have u over 2 times the integral of a squared minus u squared plus, I'm going to write this as 1/2 a squared inverse sine u over a plus c. And then we'll know we have to back substitute and we won't forget to do that. That's what I hate about them leaving these as x's. Students forget to back substitute. Okay. All right, so we have a being 10. So we're going to go ahead and write ours as u over 2. And I guess technically you could back substitute here. I'm going to do this in 2 steps, but you can do it in 1 if you'd like. A squared minus u squared is 100 minus u squared plus 1/2 times 100 times the inverse sine. U was, we'll just leave the u alone for right now, u over 10 plus c. Make sure I got everything here. And then the last thing we're going to do is back substitute, replace those u's with x's. So we had let u be sine x. So we're going to replace that with sine x. If you want to write it as 1/2 instead of divided by 2, that's what I'm going to do, but that's up to you. And it's up to you if you want to use the shorthand notation or if you want to use parentheses and show it that way. 100 divided by 2 is 50. And then we'll have the inverse sine of the sine of x over 10 plus c. Okay, that's it. We got everything. Whatever you do, be careful here. You cannot take the inverse sine of the sine of x over 10 and get like x over 10. Yes, technically the inverse sine of the sine of x is x. But when you have 10 in that expression, it all changes. You can't just pull it out because it's not just 10. It's the inverse sine with 10 in the denominator. So unfortunately, even though I know that this is screaming out at you that it wants to be simplified, you actually can't simplify that one in that way. You're just going to have to leave it. When in doubt, don't. Okay. So that's it. So you've seen 4 different types of formulas using different types of combinations of variables and functions. I'm going to assign you some homework where you can go through. Like I said, there are so many different formulas. We obviously can't cover every single one, but now you've seen how to do these with substitutions. When I specify on your test to use the table of integrals, that's what you're going to do. You're going to use the table that I've supplied for you in D2L, which is the same exact table that's in the back of your e-text. And of course, you're going to email me with questions. I have a student hour scheduled for Monday at 5 p.m., just like every Monday. I have like a once a month blood platelet donation on Mondays, but I couldn't get one this Monday. If it opens up, I might go Monday and switch my office hour to Tuesday. But I will let you know because as of right now, they don't have an opening for me, which is really sad because someone out there needs their blood platelets. My schedule is sort of restricted. All right, that is all, but Wednesday, the 20th, you'll have your test. It's going to cover all of chapter 7. Oh, and just a reminder, 7.9 is technically the last section in your text for chapter 7. It's very short because there's nothing new to learn there. Just they added it in as an additional mixed practice. Which is very similar to a chapter review, but it has a lot more exercises in it than the chapter review. So if you're wondering like, oh, should I do the chapter review? It's optional, but 7.9 mixed practice is not optional. That is actual homework that you have. And that's where you're going to have to really test your knowledge on, do I know how to use these techniques of integration? Do I know when it's most appropriate to use an inverse trig form? Do I know when it's most appropriate to use a trig substitution or integration by parts or some sort of trig integral? Those are usually a little more obvious, or partial fractions. And kind of working your way through those exercises will be an awesome way to prepare for your test, and it's technically required homework. The chapter review stuff, it's very short and it's optional. Oh, you know what though? Someone was asking me about this in the office hour. If you'd like, you might find it more helpful to actually go through the chapter review questions in your e-text or your paper text, whichever you have. You have both if you have a paper text. Because I posted on D2L the Student Solutions Manual, which covers the worked out solutions for all of the odd numbered problems in the book. So if you wanted to work your way through, it's page 571. That's where it starts, page 571. This is just review problems. I mean, they're optional, but if you were looking at stuff to do, or maybe you were looking at integrals and you were kind of like, yeah, okay, I get it. I know how to do this one, but then this one, I'm not quite sure. You might want to go through these in your book and then go to D2L. And under content, I have a student solutions manual, and it's worked out solutions that you can look through, not just for, like, for instance, any problems in the rest of the chapter, but also for the chapter review. So all of the sections in the book, so you can get the worked out solutions. So that's an option if you don't want to do the review on Achieve. And there's a lot more available to you in the book. Achieve only chooses so many things to cover, which is unfortunate, but they have a limited budget. So if you want to work on the review and if you have questions on that, also feel free to pop into the student hour and we can go over whatever math questions you have. It's not limited to homework. It's not limited to only current homework. It can be any question that you have on the whole chapter, just so that you know you're ready for your test on Wednesday. All right. I think that's it. I don't want to talk your ear off. Just wanted to make sure you had all that information. You should be good. So test Wednesday, 6 p.m. The 20th covers all of chapter 7. I'm going to put up some 7-8 homework on Achieve. Everything else should be up there ready for you. And I'll see you on Wednesday. I hope you guys have a wonderful rest of your day. And I'll see you soon.